Hello one and all, welcome to another online video by Einstein Academy. In the last lecture, we looked at learning outcomes A and B from the topic of chemical bonding from the JCH2 chemistry syllabus. In this lecture, we are going to look at 4 past year A-level questions that specifically test on these 2 learning outcomes. As a refresher, learning outcomes A is to be able to show understanding that all chemical bonds are electrostatic in nature and to be able to describe basically the 3 types of bonds that we're going to learn in the level of A-level, basically the ionic bond, the covalent bond, and the metallic bond. And as I've mentioned before, all of them are electrostatic attraction between something and something. So the definitions are all the same. The only difference is between what and what. And if it's for ionic bond, it's between oppositely charged ions, or another way that we can write it is between cations and anions that are formed as a result of the transfer of electrons from usually the metal to the non-metal. The covalent bond is the electrostatic attraction between a shared pair of electrons and the positively charged nuclei, while finally the metallic bond is the electrostatic attraction between the metal cations and the C of delocalized electrons. Candidates must also be able to draw the dot and cross diagrams for ionic bonding, such as in sodium chloride and magnesium oxide, and also for covalent bonding, such as in hydrogen, oxygen, nitrogen, chlorine, hydrogen chloride, carbon dioxide, methane, and ethene, and also be able to understand the concept of dative covalent bond or coordinate bonding, as in the formation of the ammonium ion and the Al2Cl6 molecule. Okay, so let's look at the questions that specifically test on these 2 learning outcomes. November 2007, paper 1 question 18. Use of the data booklet is relevant to this question. Which particle contains a single unpaired electron? A molecule of H2S. So the first thing, if we want to draw a dot and cross diagram of any molecule, the most important thing is always to figure out the group number in which all the elements are in. So this is in group 6. And if it's in group 6, it's 2 electrons short of octet configuration. And since it's a non-metal compound, it's a covalent bonding type of molecule, it will mean that it will form a total of 2 covalent bonds for it to obtain stable noble gas configuration. And this one, it's for hydrogen, it only has 1 valence electron, meaning that it will be able to form 1 covalent bond. Okay, and if that's the case, the sulfur must be in the middle, and it will form a single covalent bond with the hydrogen and a single covalent bond with the hydrogen. And since sulfur is in group 6, it will have an additional 2 lone pairs of electrons. And this will not be the answer. This is the dot and cross diagram of sulfur showing only the valence electrons. And this does not contain a single unpaired electron because all the electrons are paired. And hence, this is not the correct answer. Option B, one of the particles formed after the heterolytic fission of a chlorine molecule. So we haven't learned actually what's the meaning of heterolytic fission. So let me just go through briefly. You will learn this actually more in organic chemistry. So for a chlorine molecule, the dot and cross diagram looks like this, whereby since chlorine is in group 7, it will actually form 1 covalent bond in order for each chlorine atom to obtain stable noble gas configuration. Heterolytic basically means that this shared pair of electrons breaks in a way such that a single atom gets both the electrons. And if heterolytic fission were to occur for this chlorine molecule, what is going to happen is going to form this species, and it's going to form this species. Okay, so the heterolytic fission will actually produce the Cl plus cation as well as the Cl minus anion. So the question is whether any one of these particles has a single unpaired electron. So if we look at the electronic configuration for Cl+, just looking at the valence shell, it will actually be 3s2 and 3p4. And it has actually 2 unpaired electrons, and hence the Cl+ ion is not a particle that contains a single unpaired electron. The Cl minus anion, on the other hand, I'm sorry, this is actually 3p. The electronic configuration is 3s2 and then 3p6. And again, it does not contain a single unpaired electron. and hence both the particles do not contain a single unpaired electron, and option B is also not the right answer. Okay, so let me erase this for the time being to give me more space to talk about option C's and D. Just give me a moment. Okay, so the ammonium ion in NH4Cl, if we were to draw a simple structure for the NH4Cl, the structure would look like this: N, H, H, H. And then again, I hope that you remember that one of this is a dative covalent. Sorry. So the thing is that NH4 is actually a positively charged ion, which means that this will actually be the ammonium cation. Okay, whereby in fact this is actually a dative covalent bond. Okay, this is the NH4 ammonium ion, and then you have the Cl minus cation, and the Cl minus cation basically looks like this. Okay, and if you look at both molecules, they both actually have full octet configuration or full noble gas configuration, and hence the outer shells are fully filled, which means that all the electrons are paired. And as a result, no particle in the ammonium ion actually contains a single unpaired electron. And option D is also not the right answer. Okay, the final option hence must be the right answer, and we'd like to know why. The copper ion in CuO, if we look at the charge of the copper ion, because the oxygen is actually 2-, hence the charge of the Cu must be 2+. And if we were to write the electronic configuration for the copper ion, just looking at the valence shell, the Cu atom has an electronic configuration of 4s1, 3d10. Remember, this is an anomaly. By right, it's actually 4s2, 3d9. But if we were to promote one electron from the s orbital to the d orbital, we will obtain a set of fully filled d orbitals and hence achieve greater stability. And hence, the electronic configuration of the copper atom is actually 4s1, 3d10 instead of 4s2, 3d9. So for the Cu2+ cation, first of all, the first electron, we need to remove 2 electrons, and the first electron that we remove is the 4s electron, followed by removing an electron from the 3d orbital, and hence the electronic configuration of the Cu2+ cation is that of 3d9. And if you were to draw it out explicitly like that, 1, 2, 3, 4, 5, 6, 7, 8, 9, you realize that it indeed contains a single unpaired electron, and hence the copper ion in CuO indeed contains a single unpaired electron, and option D is the right answer to this question. November 2007, paper 1, question 31. Which system contains delocalized electrons? So the molecule of cyclohexane looks like this, whereby each of this vertex is a carbon atom. If I were to draw it out in its full, it will actually look like this. And then like each carbon is attached to 2 hydrogens. So I'm not going to fill in all the hydrogens, but this is how the structure will look like. But this is a covalent molecule, and hence it does not contain delocalized electrons. Graphite is a structure that we haven't talked about. We will talk about this in future. But the structure of graphite is such that you have one carbon that is bonded to 3 other carbon atoms, and you actually form sheets that are like that. Okay, this is not a very good diagram. Like the thing is that they are in stacks of sheets. So don't worry about this. Like if you don't get it for the time being, we will actually talk about the structure of graphite in the future slides. It will be covered in the later part of this in this chapter. So for the moment, if you don't get it, it's fine. But you should know that basically for graphite, each carbon is bonded to 3 other carbon in a planar arrangement. And the thing about carbon, because carbon is in group 4, right? So if it's in group 4, it means that it has 4 valence electrons. And if only 3 of the electrons is used for bonding with 3 other carbon atoms, 1 electron is actually delocalized within the entire structure. And the sea of delocalized electrons can actually act as mobile charge carriers, such that when you apply a potential difference across the graphite, the sea of delocalized electrons can actually constitute the electron current, and hence graphite is one of the exceptions of a covalent compound that actually conducts electricity. Most covalent compounds, they do not conduct electricity because of the fact that there are no mobile charge carriers. There are no charged particles, such as delocalized electrons or cations and anions, that are free to move freely within the structure. Okay, so graphite is a covalent compound. There's an exception that conducts electricity. And hence graphite indeed contains delocalized electrons, like I've explained here. Sodium is a metal. So the structure of metallic bonding is a sea of sodium is a solid lattice of Na plus ions in a sea of delocalized electrons. And hence, it is true that for sodium, it contains a sea of delocalized electrons. And hence, the answer is that 2 and 3 is correct. And option C is the answer. On to the next question, November 2007, paper 2, question 4C. Trichloromethane CHCl3, formerly known as chloroform, was used as an anesthetic in the surgery. One reason for it not being used today is that it naturally oxidizes to phosgene, which is highly toxic. So this is the equation for the oxidation of phosgene into, the oxidation of chloroform into phosgene. This is the equation for the reaction. In phosgene, the carbon atom is in the center of the molecule and is attached to both chlorine atoms and to the oxygen atom. Draw a dot and cross diagram of the phosgene molecule. So again, the important thing about carbon is in group 4, which means that it will form 4 covalent bonds. Okay, and then for chlorine, this is actually in group 7, which means that it will form 1 covalent bond. The important thing about figuring out the dot and cross diagram and the number and the structure of the molecule is always to first figure out how many number of covalent bonds each atom needs to form. This will greatly help in you solving every question. Oxygen, on the other hand, is in group 6, which means that it will form 2 covalent bonds. Okay, and now they say that the carbon is in the center, which means that, and it's bonded to, let's look at the molecular formula of phosgene is COCl2. This carbon will form 2 bonds with this oxygen, and it will form 1 bond each with each chlorine, and therefore everybody is going to form the correct number of covalent bonds. And what I mean by that is that this will be the correct structure of phosgene. And if you were to draw the dot and cross diagram, carbon will use 2 of its electrons to share with 2 electrons on the oxygen atom. Therefore, this is a double bond. And then the remaining one will be a single bond between carbon and chlorine. And of course, to be able to include all, remember to include all the electrons of the chlorine atom. Since it's in group 7, there'll be 7 electrons and 7 dots here. So this is the dot and cross diagram of the phosgene molecule. Suggest the size of the ClCl bond angle in this molecule. This is something that will be covered in the next part of the chapter, but I'll just briefly go through this. If you look at the electronic, the number of electron domains about this carbon, right? There's actually like 1 electron domain and 2 electron domains and 3 electron domains. What it means is that basically there are 3 regions of space whereby you need to put 3 different sets of electrons around the center carbon atom. And remember, because electrons are negatively charged, right, they will tend to repel each other, and repulsion always leads to destability of the destability. It means that it destabilizes the molecule. And as such, right, the principle is that we always want to maximize the separation of all these electron domains so that we reduce repulsion to the greatest extent as possible. So if we have 3 electron domains, we can prove through mathematics that the way that we can minimize this repulsion by maximizing the separation is to place these 3 electron domains in a 120 degrees arrangement. So basically, like, it looks like this, whereby every angle of this is 120 degrees. That's how we can separate these 3 electron domains maximally. And hence, the size of this Cl, C, and Cl bond, this will be 120 degrees. So this is the answer to this part B of the question. The size of the ClC-Cl bond angle is 120 degrees. Okay, on to the last question. When sodium is burned in air, a significant proportion of the product is sodium peroxide, Na2O2. Draw a dot and cross diagram showing the electrons in the peroxide anion, which contains an OO bond, single OO bond. In your diagram, use the symbols dot and cross to distinguish between the electrons from each oxygen atom, and the symbol triangle for any additional electrons responsible for the overall negative charge. So many of my students always think of dot and cross diagram as it being only dot and cross. You can only have dot and cross in your diagram, but this is simply not true. Remember, the dot and the cross is simply to represent is this electron by one atom and the cross is the electron by another atom. Why can't we introduce a third symbol that basically denotes that this electron is actually from a third atom, right? It actually makes sense to do that so that we can actually do correct accounting in the sense that we can keep track of all the electrons of where it came from. So if you look at the O2, the peroxide anion, the peroxide anion is actually O2 2 minus because of the fact that this sodium is 1 plus charge, right? So if there's two of them, it's a +2 charge, and hence the O2 must be a total charge of 2 minus. So this is the peroxide anion. The oxygen, it says that it contains an oxygen-oxygen bond, which means that this bond between the single bond between the oxygen and oxygen is a normal covalent bond whereby this oxygen shares a single electron and this other oxygen shares a single electron. If you were to add in the other number of electrons, it will be, in this case, 1, 2, 3, 4, 5, 6. So this oxygen has 6 electrons and this oxygen also has 6 electrons. However, right, if you look at this oxygen, it's actually 1 electron short of noble gas configuration, and this oxygen is also short of noble gas configuration. So it has to gain another electron, or of course you can also share another covalent bond to get stable octet configuration. But in this case, since it's sodium peroxide, it would mean that actually each sodium will actually lose 1 electron to this O2 2 minus anion. And hence, right, there will actually be 2 triangles here, and this triangle is actually the electron that is from sodium. Okay, so that's why there are 3 symbols here. The cross represents the electrons by this oxygen atom, the dot represents the electron by this oxygen atom, while the triangle represents the electrons that is lost by the sodium atom. So this is the dot and cross diagram of the peroxide anion. Okay, the final question: when sodium oxide is added to water, an alkaline solution of hydrogen peroxide is produced. Write an equation for this reaction. So basically we have Na2O2 and we add it to water and we produce hydrogen peroxide. And because they say an alkaline solution is produced, right, it would mean that NaOH is also produced. So let's see if we can balance this equation. So I guess we need a 2 here, and then we need a 2 here. And this will be the full balance equation. 2 sodiums, 4 oxygens, and 4 hydrogens. Okay, so this is the balanced chemical equation for the reaction when you add sodium peroxide to water. Okay, I hope this with these questions, you now understand how we can apply the concepts that we learned for these two learning outcomes to the questions in the A-level syllabus. And I hope you all enjoyed this video. So if you like this video, please hit the like and subscribe button for me to make more interesting videos for you guys. And thank you very much for tuning in. And I'll see you next time again.